So let's dive into a couple of these examples. You already have a good definition of what an isotope is. An isotope is a version of a certain atom or a certain element. So thinking that way, all of them will have the exact same number of protons because they're the same element, but they end up with a different number of neutrons. And so what we'll see is the total of protons and neutrons vary. And that proton-neutron total is the mass number. And so that's what we're focusing in on here with our visuals and our calculations. So we're working together in this little review here, number 7 and number 8. So we've got 3 diagrams. We want to for sure make note of what we're looking at. These green on the energy levels are of course, our electrons. These reddish orange are the protons. And the bluish ones here, neutrons. So we're looking at 3 isotopes of carbon, meaning they are all the same element, carbon. So when I think about the amounts of protons, neutrons, and electrons, I should for sure have something consistent. And I know no matter what, every isotope, because it's the exact same element, will always have the same number of protons. So when I'm looking at my visuals, I've got 1, 2, 3, 4, 5, 6 protons here for carbon. I should automatically verify 3, 4, 5, 6 here, and also 3, 4, 5, 6 here. Because that's what makes it carbon. So those protons have to be consistent. But what's different among each one is this, our mass number. And you might remember that mass number is the total of protons and neutrons inside the nucleus. So if we have 6 protons every single time with a varied mass number, I know my number of neutrons is going to be changing. And I can simply count it, or I can do a calculation, right? Let's do a little bit of both. So the first one here, let's count our neutrons. Neutron, of course, being a 0 charge, so I have 1, 2, 3, 4, 5, 6 neutrons. So in verifying what that is, those 2 should equal my mass number. Here, I have a mass number of 13. So I'm going to go a different route here. Again, these 2 should total 13. So if I do a little calculation, that should tell me I end up with 7 neutrons. Because I might have an example where I don't have the chance to count these out. In my final example, I don't have a mass number indicated. So that's something that I need to be able to calculate. And so in order to do that, I do need to then go back and count my neutrons. 1, 2, 3, 4, 5, 6, 7, 8 neutrons here. Again, totaling these up gives me the mass number, which in this example is 14. Again, all of these are the exact same element. They are just different versions due to a change in their mass by more or less neutrons. Now our final down here is the electron. We know electrons are the particles circling the nucleus on the energy levels. We can't unfortunately look at a calculation to determine electrons, but we can consider 2 things. All of these are listed as atoms, so I know in an atom my protons equal my electrons because the overall charge is neutral. So I can consider that they'll be equal, but because I'm looking at the diagram, I can also count to verify. 1, 2, 3, 4, 5, 6. Same thing here, 3, 4, 5, 6, and again, 3, 4, 5, 6 here. Now, when we think about overall similarities and differences between isotopes of an atom, we're looking for 2 things that are the same across the board and 2 things that are different across the board. So the biggest thing to really think about is what makes it carbon, okay? They are all the same element, but then why? Okay, so what was defining this? And the other thing to think about then with differences is what makes them isotopes. Even though they are all the same element, what about them is different? And that gives you a couple different opportunities there as well.